So now we come to the third and final step of the Karnaugh map problem, and that is to write the equation that comes from the groupings that we established in an earlier step. Now I am going to go ahead and use the same groupings that I developed in the previous video example. So we have here a grouping of these two, and this one is wrapping around, and then I have a grouping right here. And so then the question is, what is the equation that corresponds to that? Well, let's consider how many terms are there going to be, how many products are there going to be. There are three groups, so therefore there'll be three products. You can see, let's take this the cell 0 and 1 first. So this grouping on the top left corner. Those both belong to the row that corresponds to C equals 0, and they also both correspond to the left half of the table that corresponds to A equals 0. So if I'm looking here to write an equation for F is going to have three product terms. The first product term is going to be this grouping of cells 0 and 2, and that corresponds to not A and not C. So that's the first term, is coming from the top left corner. Let's take the group that wraps around from the top left corner to the top right corner. Well, those are also going to belong to the row that corresponds to C equals 0. And then they are also both going to have B equals 0. So both of those cells also contain B being equal to 0. So this is or not B and not C. So each group forms its own product term, and we just have to identify what is common about amongst all of the elements of that product term. Now, unfortunately, cell number 7 has to be grouped completely by itself. What does that cell have in common? Well, it belongs to the column in which A equals 1 and B equals 1 and C equals 1 for that row. So this is or A and B and C. Now, one good thing to know is that although this is the simplest and most optimized, most efficient sum of products expression that we can have, it is not necessarily the most optimized equation overall. Notice, for example, I could factor a C bar out of this equation. It would become A bar or B bar or A and B and C. And then if you start to get extra fancy, you could, for example, realize that De Morgan's theorem could turn that into a NAND gate and so forth. But to be honest, at this point, you've seen K-maps for about an hour and a half. So let's go ahead and stick with this as our best answer for part A of this example. Okay, then we have another example. Again, this is the same one that came from the video last time. So I have the group that is the left-hand column. I have this small group near the middle. And then I have the four corners. And so I need to figure out what is the equation that corresponds to those three groups. Again, three groups, that means three product terms. Let's go ahead and take the left-hand column first. So the left-hand column is going to belong to the place where A equals 0 and B equals 0. So we have A equals 0 and B equals 0. Therefore, this is not A and not B. That's the first group. Let's take the second group to be cells 7 and 15. Well, they belong to the row where C equals 1 and D equals 1, and then they belong to the middle two columns, which is where B equals 1. So B equals 1 for both of those. So therefore, this is or B and this is C and D are both 1, C and D. And then we just need to hit the four corners. Let's see, what do the four corners have in common? Let me get some of this other previous stuff out of the way here. Okay, what do the four corners have in common? Well, they both belong to this column and this column, which is where B equals 0. And they belong to the top row and to the bottom row. And in both of those cases, D is equal to 0. So I have D equals 0, D equals 0, and then I have B equals 0, and I have B equals 0. So this is not B and not D. So that's the full expression. We have three terms that came from the three groupings. You can see that groups of 4, we had two groups of 4. Those two groups of 4 yielded terms that only had 2 elements in the product, but a group of 2, well, that yielded a larger expression. It yielded 3 variables in the product, and that's why we want the largest groups possible. We want the fewest groups possible to have the fewest number of terms. We want the largest groups so as to make each of those terms be as simple as it can be.